Welcome back. All right. So let's get to what is this slide, Sam? I'm pausing because I don't. Oh, they give these problem solving strategies. Yeah, like you wouldn't read the problem carefully. Draw a diagram if possible, right? Introduce notation. Yeah. I don't know. Yeah. This is the route that they say you should take. These are the steps that you should take. Read the problem carefully. No, read it carelessly. Draw a diagram. I love to draw a diagram. I don't know. My brain it works better if I can see the problem. We introduce notation. That's kind of me saying like, what do we know? What do we don't know? Express the given information the required rate in terms of derivatives. Yeah, that's like saying, okay, we know dx dt. We're solving for dy dt, whatever. Write an equation, and step 5 is really like the difficult part. Write an equation that relates the various quantities of the problem together. If necessary, use the geometry of the situation to eliminate one of the variables by substitution. That's like what we did in that similar triangles problem. Sometimes if you can figure out a way to remove a variable so that you don't have to apply the derivative to it, that actually helps you in the long run. Step 6, actually differentiate. Don't forget to use the chain rule, implicit differentiation. And then substitute the given information into the resulting equation and solve. So let's do that process. Okay, here we go. 3 more problems to do, right? Oh, no, just 2. I'm sorry, just 2. Just 2 today. We got 2 cars. Car A is traveling westward at 50 miles per hour. Car B is traveling north at 60 miles per hour. They are both headed for the intersection of the 2 roads. At what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection? I tried to read that carefully. All right, now let's draw a diagram. Okay, car A is traveling west at 50 miles per hour. So we see this intersection here, right? Oops, pen, please. We have this intersection. Car A is traveling to the west. So here's car A, right? We'll put there's car A. Okay. Car A is traveling west at a rate of 50 miles per hour. Okay. I'm going to treat this like, since they're both going at each other, I'm going to treat their rates as like negatives. Okay. So I know this rate is 50 miles per hour. So I'm going to say it's going in at 50 miles per hour. Now, since it's our left and right, I'm going to call that our x component. We're going to say that is dx dt. dx dt. dx dt is negative 50 miles per hour. That's our rate. Car B is traveling north. Okay. So here's car B down here. We are traveling north at a rate of 60 miles per hour. So I'm going to say d, since it's the vertical component, dy dt is going to be negative 60 miles per hour. Again, I'm treating them as negatives because they're moving in. If you treat them as positive, it'll work out the exact same. You just got to, figure out your answer in the long run. In the end. In the end, your answer might come out negative, and you just got to know that it's going to be positive. Now, what really are we trying to find? We are trying to find at what rate the cars are approaching each other. At what rate are the cars approaching each other? That is this, right? As I bring the cars closer and closer together, what happens to that red line? It gets smaller and smaller and smaller, right? The cars get closer and closer together. So therefore, the rate of that red line changing is what we are looking for. At what rate are the cars approaching each other? So let's call this component a z. Yeah, we used x and y, so now we use z. You want to call them a, b, and c, whatever. Okay. So we'll call that z. So we are looking for dz dt. That's what we want to know, right? That's what we want to know. Now, when do we want this thing to happen, right? We need to know what time we want to, and when I say what time, I'm saying, okay, in terms of miles. At what moment do we want this thing to happen? We want this thing to happen when x is 0.3 and when y is 0.4, right? Car A is 0.3 miles and car B is 0.4 miles. Okay. Now, how do I relate x, y, and z together? Pythagorean, right? Pythagorean. X squared plus y squared equals z squared, right? I can relate those together. And if I differentiate this entire equation, do I have a dx dt? Yeah. Do I have a dy dt? Yeah. I'm looking for dz dt, right? So it's perfect. I want to differentiate the z. So yeah, I don't want to remove any equation or any variables here. All right, so let's differentiate. This is going to be 2. Oops. This is going to be 2x dx dt, right? Or if you wanted to say 2x x prime, yeah, that's the same thing, but I'm going to call it dx dt. 2x dx dt, that's the chain rule, plus 2y, that's the derivative of the squared, times y prime, or dy dt, is equal to, same thing, 2z dz dt. And we have pretty much everything we need. Let's start plugging in and figure out if we need anything else. Okay, so this is going to be 2 times 0.3 times negative 50 plus 2 times 0.4 times negative 60 is equal to 2 times, now how do we figure out what z is? Pythagorean again, right? At the instantaneous moment of 0.3 and 0.4, what is z? Well, that's a 3, 4, 5 triangle, 0.5, right? 0.3 squared plus 0.4 squared is equal to c squared. 0.3 is 0.9. 0.3 is 0.9. 0.4 is 1.6. Add them together, 2.5. Square root 2.5, you get 0.5. But again, it's a 3, 4, 5. 2 times 0.5 times dz dt, which we don't know because that's what we're trying to find. Look, an entire equation with just dz dt in it. Let's start to solve. Okay, 2 times 0.3 times, oops, that's the wrong way, times negative 50 plus 2 times 0.4 times negative 60, negative 78, and we divide by 2 times 0.5. Oh, because that's 1. I was like, what is it? Negative 78. Negative 78. So that means dz dt is negative 78. Why is it negative? Because again, they're coming closer together, right? That is making the rate. I'm sorry, the distance is closing in on one another, so the rate at which it's changing is going to be negative. So that's why we say it's the negative again. So negative 78 is dz dt. Let's figure out what the units are. Well, again, this is all in miles per hour. So negative 78 miles per hour. If you gave me 78 miles per hour, that would be totally fine. If you just used the positive, that would be fine. Questions about that one? So that one solely relied on the Pythagorean theorem. We didn't need any additional equations or anything like that. Just the Pythagorean theorem. All right, let's take a look at one more, shall we? Let's do it. A man walks along a straight path at a speed of 4 feet per second. A searchlight located on the ground 20 feet from the path is kept focused on that man. At what rate is the searchlight rotating? When the man is 15 feet from the point on the path closest to the searchlight. Let me read that again carefully. A man walks along a straight line path. Oh, there he goes. He's walking along this path. He's moving at a speed of 4 feet per second. A searchlight located down here, located on the ground 20 feet from the path, that's 20 feet right there, is kept focused on the man. So as he walks away, I keep rotating that light so that it's focused on that guy. At what rate is that searchlight rotating when the man is 15 feet from the point on the path that is closest to the searchlight? The closest point on the path is the perpendicular. Right? The closest point on that path is the perpendicular. So that's why we say when he is 15 feet from the point on the path closest to the searchlight, that's going to be 15. All right, let's label our diagram. This diagram is given to us. So let's label everything that we know. A man walks along the straight line path at a speed of 4 feet per second. In terms of the notation, what do you want?
I wanted to rant for a second.
Come on in.
No, I want to hear this problem.
Really? I mean, this one is going to take a while. Are you sure?
I got time.
Okay, perfect. Okay, so in terms of the notation here, what is 4? In terms of the notation here, what is 4? dx dt. Good. So dx dt is 4. The rate at which he is walking is 4. A searchlight located 20 feet from the path here is kept focused on the man. At what rate is the searchlight rotating? So what are we looking for? In terms of this notation, what are we looking for? It's a rate, right? So it's got to be a d something, right? The rate at which it's rotating. The rate at which the angle is changing, right? So d theta dt is what we're looking for. That's what we want to know. When do I want to know that? I want to know that when x is 15, right? The moment x hits 15, I want to know how fast is that angle changing. That's what we're asked here. Now, how can we relate theta x, and this 20 together? How can we do that? Tangent. Yeah, good. Tangent. So tangent theta. Did you get that one?
Yeah, I was good with that.
Yeah, you good with that?
I'm following along.
Tangent is opposite over adjacent, right? So x over 20. Okay, can we differentiate now? Because in the end here, look at my variables here. Do I have to remove any variables? Do I have to get any variables out? Well, I'm going to get a d theta dt, right, when I differentiate this. I'm going to get a dx dt when I differentiate this. I have a dx dt. I'm looking for the d theta dt. So there's no extra variables within this that I need to get out before I differentiate. All right. So let's find what is the derivative of tangent? Who remembers? Look at you. Proud of you. It's probably because he just did that homework assignment. He's still back on that.
Yeah, I finished 3 form before you came back to school.
Look at you. Secant squared. Secant squared theta. Now, I'm going to treat this as like a 1/20th x, right? That's like the constant sitting in front of it. So it's really just, let me move this down a little bit. Oh, whatever. So it's really just a 1/20th dx dt. Right? Because the derivative of x is just 1. So there's no real chain rule going on. It's just 1/20th dx dt. Oh, what did I forget? Oops. What did I forget? Tell me. The d theta dt. Good. Yeah. I was so proud of you that I missed the moment. Secant squared theta is the derivative of tangent, but then I have to include the d theta dt. Okay. Now we're good.
You didn't even have a cheat sheet. You couldn't get that written down correctly.
Jeez. I'm not looking at that.
Oh, okay.
I'm doing this
Hey,
whole
everybody,
thing.
you guys should be, petitioning for, hey, we get our cheat sheets on.
I think somebody said that earlier
Yeah,
on.
we tried that.
Mr. Laverick gets to hold his notes.
I did that whole lesson cold turkey when they said that.
I mean, I
Okay.
taught substitution.
I'm teaching three different I'm teaching three different.
I taught substitution today. I didn't need a cheat sheet.
Yeah. Yeah. If I taught fractions all day, I wouldn't have
Hey,
cheat sheet
I
either.
didn't need a cheat sheet. I'm just saying.
You want to teach us? No cheat sheet here.
Oh, there's fumbling things now. We got him.
You want to finish this one off?
Let me see the end of this example first.
Right.
Oh,
This is the last one.
It's okay, then. I'll go back to substitution.
Yeah, right. I actually did I know. Oh yeah. Okay. Now I remember. Because what's unknown? What's unknown? Right? Theta. We don't know what theta is. Right? I can plug in like secant squared. We don't know this. Right? What is d theta dt? What we're looking for? We have a 1/20th times dx dt, which is 4. Can we figure out theta when x is 15? Yes. Because is 20 changing at all? No. 20 is going to be constant, right? 20 is going to be constant. This is going to be at that 15, right? So what is theta in terms of that 15 and 20? Well, theta, what do we want to say here? What did I use cosine? I used cosine, but I don't think I needed cosine here. Yeah, I don't need cosine. Because what am I going to use? Tangent again, right? Because I know tangent theta is opposite 15 over adjacent 20. So theta is equal to inverse tangent of 15 over 20. So what is the angle? Let's figure that out. Make sure I'm in radian mode. Perfect. We got inverse tangent of 15 over 20 is 0.644. We'll just say 0.64. So theta is 0.64. Perfect. Right? Okay. Now, what is secant? 1 over what? What is secant? 1 over cosine, right? 1 over cosine. So this is going to be 1 over cosine 0.64 squared, d theta dt, and then 4/20 turns into 1/5, right? 1/20 times 4. So really, all I need to do is take 1/5 and multiply by cosine of 0.64 squared. Let's do that. 1/5 times cosine of 0.64 squared. There it is. 0.13. D theta dt is 0.13. Now, what is our label in this case? Well, what's our time label? Per second, right? What do I label an angle? But did I do degrees? Radians. So this is actually 0.13 radians per second. 0.13 radians per second. That's the speed at which the... Perfect. Oh, relax. That was fun. All right. So you have a little bit of time today to start working on your assignment. Again, you have all day tomorrow to work on those problems. Ask questions where you need to, and I will help you.
3.9 or like 3.6? Oh, okay. 3.6 is over.